Hi, I'm Darshana Sharma, and here's my presentation on Lab 2, which is the charge tape revision. So the purpose of this lab was to compare point charge model to lines of charge model, and this is done by using the properties of superposition, which is dividing a charge object into pieces and adding the electric fields of each of those segments to find the net electric charge of the object. And helps us understand the effects of charge when distributed over a shape and not at a single point. So a preview of my results is that force of gravity, which equals electric force, is 1.92 times 10 to the negative 3 newtons. And the charge on each tape is 4.9 times 10 to the negative 8 coulombs. And this shows me that the results are more accurate using the properties of superposition as opposed to treating the tape as a point charge. So the models and fundamental principles used are Coulomb's law, and we're treating K as 9 times 10 to the e to the positive 9 Newton meter squared over Coulomb squared. And this formula helps in the calculation of a point charge. The second formula we're going to use is electric field distributed over a rod formula, and this requires knowledge of the length of the rod, which is going to be the tape, and the distance between the charges is perpendicular from the center of the tape. So the observed model used in this experiment is that the system is tape B, which is a suspended U-tape, and the surroundings tape A, which is a U-tape being held up to tape B. And the initial conditions are listed below, and each piece of tape is modeled as an individual segment with equal charges. And for this experiment, we're going to assume that each tape has equal charge and that the charges are equally distributed across each tape. So to set up, we charge both the tapes, then hang them up, hang tape B up, and hold up tape A to observe how it affects the charges. And we see that tape A causes tape B to move up, and the separation distance is 0.075 meters. So here's a free body diagram specifically showing what's going on with tape B. So we can see that each of the segments have an individual charge moving upwards. So the net charge of this electric field is moving upwards for the electric force, and that the force of gravity is bringing tape B down. And this opposes tape A, which is being held up to tape B, which is the upward force. And the electric force from tape B acting on tape A is pushing tape A down. So here we can see the net force is zero as both electric forces cancel each other out and as they're acting on each other. So here are known values, and first I calculate the weight of the tape using F of G equals mass times gravity, which gives me 0.00196 newtons, and I can calculate the charge on the tape, the point charge, using and the answer it gives me is 3.5 times 10 to the negative 8 coulombs. And again, this is the point charge of the tape. So here's my computational model. So as you can see, I have all my constants listed here, and then I use a function. And as you can see, I have three Q values, and this will be explained at a later time, but we're using 4.9 times e to the negative 8 as it's a more accurate Q value. So first I create the function for the electric field, and I calculate magnitude of R and R hat, and I plug that into the formula. And then I calculate the function creating a line of charge here. And then here I create the tapes using by modeling it in my computational model, and then I calculate the electric field and the electric force acting on both the tapes. And then I calculate the net electric force and the gravitational force, and I create the arrows to complete my model. And here is my first computational model, and I use the point charge 3.5 times 10 to the negative 8 coulombs. So as you can see, this model is not completely accurate as the force arrows are not equal, therefore are not canceling each other out, whereas we know F net equals 0. So then I recalculated using the electric force of the rod, given my values and length of the tape, and here I got 1.1 times e to the negative 8 coulombs, which is even more inaccurate as the arrows are definitely not canceling each other out. And then with some trial and error, I was able to get the arrows to cancel out using 4.9 times e to the negative 8 coulombs. So some similarity and differences. First of all, there were different Q values between model lab 1 and lab 2. However, they both show accurate force relationships, F net equals 0. But again, there are different charge values. I believe this lab 2 is more accurate model compared to lab 1, as the whole tape realistically shouldn't be considered a point charge. And this helps me better understand how forces cancel out between tapes. And some potential sources of error are that the charges are not equally distributed across each tape, incorrectly measuring the observational values, meaning the length between tape A and B and the length of the tape, and that the charges on each tape aren't equal, so they affect each tape differently, and each segment acts differently. So if I modeled each tape as a single point charge, the value of lab 1 was 3.5 times 10 to the negative 8, and for my lab, which was a point charge model, and for lab 2, which was a line charge model, I got 4.9 times e to the negative 8. So there's a 33.3% difference. However, I believe the line charge model is more accurate. I believe it's because these values are different as different formulas and methods are being used in calculating these charges. And I believe the value produced from modeling the line charge, aka lab 2, is more accurate as it considers the length of the tape. It's more realistic to how these charge objects interact, as tape realistically isn't a point charge and the charges are distributed across the entire tape. So it should be treated by using the properties of superposition. Thank you.